Good evening, and welcome back to this quiet corner of the night sky. Tonight, we are traveling outward to one of the strangest worlds in the solar system. Most planets keep a familiar posture as they circle the sun, leaning only a little. Uranus does something else entirely, and it does it with almost sleepy confidence. It turns with its whole body tipped so far over that it seems to roll. One pole faces sunlight for ages, while the other waits in a darkness just as long. Something happened to this planet very early, and the evidence still hangs around it. If you enjoy slow journeys through space like this, subscribing is always appreciated. And for now, you do not need to figure anything out or hold on to anything. Just settle in, let the day loosen its grip, and we can begin. If you lined up the major planets like spinning tops across a table, 7 would look broadly familiar. Their axes tilt by different amounts, but most still appear more upright than not. Uranus would be the one top already knocked over, still spinning, somehow calm about it. Its axis is tilted by about 98 degrees, which is almost a full right angle. That number can sound technical, until you pause and really picture what it means. This planet is not simply leaning harder than the others in some exaggerated version of normal. It has gone past normal entirely and entered a category all its own. I think that is part of why Uranus feels so quietly memorable once you really meet it. It is not the loudest planet, but it may be the one that most completely ignores expectations. And tonight, that sideways posture is the thread we will follow. Here on Earth, our axis is tilted about 23.5 degrees, and that modest slant gives us seasons. Summer stretches long in one hemisphere, while winter gathers in the other. Then they trade places. Mars leans by a similar amount, so its year also carries a recognizable seasonal rhythm. Saturn and Neptune tip a bit more, but still keep a generally upright stance. Jupiter, by contrast, barely tilts at all, as though it never bothered to lean. Against that backdrop, Uranus looks almost impossible, as if a rule was broken in private. At about 98 degrees, its axis lies nearly flat within the plane of its orbit. That is why people often say Uranus rolls around the Sun rather than simply spins. It is a vivid description, and for once, the vivid description happens to be fair. Even among planets where strangeness is common, this is an especially elegant kind of odd. Because Uranus has tipped slightly beyond a perfect right angle, astronomers describe its rotation as backward. In formal terms, it spins in the opposite sense from most of the major planets. Venus also rotates that way, though almost certainly for a very different reason. The bookkeeping matters less than the picture underneath it, which is simple and striking. Uranus is the one large planet in the solar system that lies down instead of standing up. Today, that fact feels peaceful, almost graceful, because the violence that may have caused it is long gone. What remains is a pale blue-green world turning quietly in the far cold. It does not look damaged or troubled or unfinished in any visible way. It simply keeps its unusual posture with the patience of something ancient beyond imagination. And that calm after the mystery is part of what makes the planet so easy to linger with. Nearly every other unusual feature of Uranus seems to trace back to that same tipped axis. Its seasons become extreme because the sunlight falls across it in such an unfamiliar pattern. Its rings and moons are arranged in a way that reflects the planet's strange orientation. Even the puzzle of its missing internal heat may connect back to the same old event. In that sense, asking why Uranus lies on its side is not a narrow question. It is really a way of asking how this entire world became itself. I always like planets most when one feature quietly explains a dozen others. Uranus offers that kind of unity, where one ancient tilt seems to echo through everything. The mystery is not a decorative detail attached to the planet from the outside. It is more like the hinge on which the whole story turns. Uranus belongs to a pair of planets astronomers call the ice giants. It and Neptune make up the smaller, more distant duo among the four giant outer worlds. Uranus has about 14.5 times Earth's mass, which is enough to make our planet feel very small. It is enormous by human standards, though still clearly outscaled by Jupiter and Saturn. The term ice giant can sound simple, but it hides a very alien kind of interior. These planets are built largely from water, ammonia, and methane in exotic high-pressure forms. Around that deeper material sits a thick atmosphere of hydrogen and helium. There is no solid surface there waiting like a shoreline beneath the clouds. I find that detail especially useful because it reminds us this is not a bigger Earth. It is a fluid world with a posture stranger than any rocky planet could comfortably carry. Uranus also holds a special place in the history of discovery. The planets out to Saturn were known in antiquity because they can be seen with the naked eye. Uranus sits near the edge of unaided visibility, faint enough to be mistaken for a star. It was the first planet recognized only after the telescope entered human life. In other words, it arrived as a genuinely new member of the solar system. That gave it a different kind of introduction than the older, brighter wandering lights. For a while, though, even after it was found, its strangest secret remained hidden. From so far away, Uranus looked like a small, smooth disk with very little to reveal. Its bizarre tilt was not obvious at first glance, and that feels fitting somehow. A planet this unusual did not announce itself all at once. Once astronomers realized Uranus was lying nearly on its side, the planet changed character completely. It stopped being merely distant and became the great exception among the major worlds. 7 planets, more or less, follow the family pattern, though each with its own small variation. Uranus breaks that pattern almost as dramatically as a planet possibly can. A world can only be tipped so far before it is essentially lying flat. Uranus sits right at that edge, and even a little past it. That rarity matters, because uncommon outcomes usually point back to uncommon histories. Planets form from a broad, spinning disk of gas and dust, which naturally encourages shared alignment. So when one world ends up this far askew, something probably happened after its birth. The sideways posture is not just interesting by itself. It is evidence that the ordinary story was interrupted. The leading explanation is an ancient collision, and it remains the favorite for good reason. Early in the solar system, giant worlds were still forming in a crowded and unruly environment. Leftover planetary building blocks crossed paths, merged, scattered, and occasionally struck with enormous force. In that rough early era, Uranus may have been hit by a body several times Earth's mass. Not a direct smash, but a glancing blow delivered at exactly the wrong angle. That kind of impact could have tipped the whole planet over without tearing it apart. It is a dramatic idea, yet it fits the scale of the problem surprisingly well. To reorient a world that massive, you need something more than a casual nudge. And the young solar system, for a brief while, was full of objects capable of providing one. Still, that is not the only possibility, and the quieter alternatives have not vanished. Some researchers have wondered whether a large moon, now lost, slowly tugged Uranus into its sideways stance. Others explore whether long gravitational effects, acting patiently over immense spans of time, could have done the job. Those ideas are gentler than a giant impact, and that gives them a certain appeal. They remind us that not every dramatic result requires a dramatic moment. But for now, the collision explanation ties the facts together most neatly and most persuasively. It offers one strong event that could account for the tilt, and perhaps much else besides. We will come back to those competing possibilities later, because the question remains honestly open. For tonight, it is enough to hold the mystery in its proper shape. Something laid Uranus down near the beginning, and the planet has stayed that way ever since. Before we ask what did it, though, we should ask how astronomers learned that posture at all. That question turns out to be gentler than it sounds, because Uranus does not reveal very much at first. From our point of view on Earth, it appears as a small, pale blue-green disk suspended in darkness. There are no bold stripes like Jupiter's, and no bright, easy cloud belts like Saturn usually offers. For a long time, that smoothness made the planet feel almost blank, like frosted glass seen far away. A world with so few markings does not easily tell observers how fast it turns or leans. Even measuring its rotation took patience, because astronomers had so little visible texture to follow around. The best estimate eventually settled near 17 hours for one full spin of the planet itself. That is a fairly quick day for such a distant giant, though distance makes everything seem slower. I have always liked how a planet can be active and elusive at exactly the same time. Uranus keeps moving faithfully, while giving almost none of the visual help other planets provide observers. Its extreme tilt also changes what we are able to see of the planet across many decades. For long stretches of its 84-year orbit, one pole angles toward the inner solar system and toward us. That means we can spend years, even decades, looking mostly down onto one broad hemisphere alone. The opposite half remains turned away, hidden in a darkness that our telescopes cannot simply peer around. Only near the equinoxes does the geometry relax and let both hemispheres come better into view. Then the equator faces us more directly, and the planet looks less like a cap and more balanced. This matters because perspective shapes knowledge, especially when the object being studied changes so slowly over time. A cloud feature near one pole may be conveniently placed for years, then disappear for years again. Astronomy often feels less like hunting answers than waiting for the room to rotate into better light. Uranus teaches that lesson especially well, because even seeing it properly depends on season, angle, and extraordinary patience. So the posture of Uranus was not read from the disk alone, however carefully people stared at it. The clearest clues came from the company around the planet, especially its moons and its rings. As a general rule, moons and rings orbit close to a giant planet's equator rather than randomly. That makes sense, since planets and their nearby systems form from flattening, spinning material gathered together. If you can determine the plane where the moons travel, you can infer the planet's equator. And once the equator is known, the tilt of the spin axis follows naturally from that. This is one of those wonderfully indirect methods that science uses when direct answers stay out of reach. The planet itself may look quiet and unreadable, but its companions quietly give away the arrangement. It is a little like learning the direction of wind by watching leaves move in silence. Uranus kept the same rule as other planets, but the rule pointed somewhere far stranger in practice. Its moons circle where they should, around the planet's equatorial plane, and the rings follow that same orientation. But because Uranus itself is tipped almost sideways, that entire equatorial system is tipped with it. Instead of wrapping around an upright world like a flat belt, everything orbits in a steeply turned plane. From far away, this creates views unlike those of any other major planet in the solar system. Sometimes, from our point of view on Earth, the Moon system opens toward us almost face-on. When that happens, the moons appear to trace nested circles around the planet, one inside another. The pattern looks a bit like a target, or even a dartboard, centered on that pale disk. An ordinary, more upright planet would not present its moons this way during the same viewing geometry. That visual signature is quiet but unmistakable once you understand what the circles are really saying. The planet does not announce its tilt dramatically. It lets geometry whisper the answer over time instead. At other times, the same tilted system turns edge-on, and those broad circles collapse into a narrow line. Then the rings become a thin stroke, and the moons seem arranged almost straight across space. Face-on versus edge-on is a simple phrase, but it captures a beautiful change in perspective. Across the decades, Uranus moves along its orbit and slowly carries that whole arrangement between those views. The target opens, then closes, then opens again, but on a schedule measured in human generations. No single observer sees the full cycle quickly, which gives the planet an almost geological slowness. That slowness is part of why certainty took time, and why the conclusion feels carefully earned. Astronomers were not relying on one dramatic photograph, but on many observations spread across years. The evidence accumulated gently, each season adding another small piece to the larger three-dimensional picture. By then, Uranus had gone from anonymous bluish dot to the strangest spinner among the major planets. The rings confirmed the same story, and they were discovered in a wonderfully understated way. Uranus does have rings, but they are nothing like Saturn's broad, bright architecture of reflected sunlight. These are dark, narrow bands, thin and difficult to see directly against the black around them. They first revealed themselves through an occultation, which simply means the planet passed in front of a star. As that happened, the starlight blinked out briefly several times before the planet itself crossed the star. Then, after the planet moved past, the star blinked again in the same quiet pattern. Each short disappearance marked one narrow ring intercepting the light along our line of sight. I find that method deeply satisfying, because it feels like learning by listening rather than staring harder. The rings were not discovered by spectacle, but by noticing interruptions in a distant point of light. And those interruptions showed that the rings, too, were aligned with the same tilted equator. That agreement between moons and rings is what made the case so persuasive to astronomers. Different kinds of evidence were all pointing toward one arrangement, and none of them contradicted the others. The moons traced a steep orbital plane, and the rings occupied that same plane around the planet. The changing appearance of both systems over time matched what a sideways world should produce exactly. Even the rotation period made more sense once the larger geometry had been pieced together carefully. This is how astronomy often works, when the object itself refuses to be easy or generous. You gather small signs, compare them patiently, and wait for the pattern to become unavoidable. There is something almost restful in that method, because it rewards steadiness more than dramatic inspiration. Uranus was not decoded in a flash of genius, but through long attention to faint details. A planet that hides its face can still be understood, if you are willing to study everything around it. It is worth pausing on how much patience that kind of knowledge really asks from people. A tilted axis, nearly lying flat, cannot be measured from one glance or even 1 year alone. You need repeated observations, changing viewpoints, orbital tracking, and a willingness to let time participate. The universe rarely hands over its structure all at once, and perhaps that is part of its charm. With Uranus especially, the answer emerged like a photograph developing slowly in a darkroom tray. First came the faint disk, then the rotation, then the moons, then the rings, then the geometry. Each result made the next one easier to trust, until the whole arrangement locked into place. By then, the sideways posture was no longer a strange suggestion, but a measured fact of nature. Science can sound cold in summary, yet the process often feels almost tender in real practice. You watch, you wait, and eventually a distant world consents to become a little more known. And still, knowing that Uranus lies down is not the same as knowing what laid it there. Observation can tell us the posture with confidence, but it cannot directly replay the ancient event itself. The cause belongs to a much earlier solar system, crowded, unfinished, and hidden behind billions of years. That is where the mystery changes character, from geometry in the present to history in the deep past. Before we reach for that cause, though, there is another question worth lingering over first. What does a sideways axis actually do to a planet during a year that lasts 84 Earth years? It changes far more than appearance, and the consequences reach into light, darkness, weather, and time itself. A tilt like this is not just a statistic attached to the planet from outside. It becomes the rhythm by which the whole world experiences sunlight, shadow, and the passing of seasons. And once you follow that rhythm, Uranus begins to feel stranger than any diagram first suggests. Because Uranus is tipped so far over, its seasons are not simply stronger versions of Earth's familiar pattern. They are built on a completely different layout of sunlight, one that reshapes the meaning of day. For long portions of the orbit, one pole points almost directly toward the sun for years. The other pole points away and remains in darkness just as long, receiving no sunrise at all. Near equinox, that arrangement changes, and sunlight spreads more evenly across the globe for a while. Then the planet's 17-hour rotation produces something closer to ordinary day and night over broad regions. But near solstice, the same rotation no longer gives the poles sunrise or sunset in any normal sense. The sun circles in the sky without dropping below the horizon, or never appears there whatsoever. I think this is where the tilt stops sounding unusual and starts feeling genuinely difficult to imagine. A planet can be measured calmly, yet still remain emotionally strange once you picture life under its sky. So the real mystery waiting ahead is not only what tipped Uranus, but what that tipping has done. It has stretched seasons across decades, rearranged where light falls, and altered how the atmosphere behaves. It may even connect to why the planet seems oddly cold compared with its near twin, Neptune. Once you know how astronomers discovered the sideways posture, the next step feels almost inevitable. You start wondering how a world lives after being placed in such an unfamiliar orientation. That question leads away from telescopes and viewing angles and into the long year of the planet itself. There, the geometry becomes climate, and the posture becomes experience, if a planet can be said to experience. The evidence stops being only visual and starts shaping the whole life of the world. And that is where Uranus becomes less like a curiosity and more like a fully different kind of place. So now that we know how the tilt was found, we can finally ask what that tilt does. And what that tilt does is turn a year into something almost unrecognizable, even by planetary standards out there. Uranus needs about 84 Earth years to complete one trip around the Sun, moving slowly through immense cold. That means a single season there can outlast whole generations here, which always makes the imagination feel undersized. On a more upright world, even a very long year would still preserve the familiar rhythm of sunrise and sunset. But Uranus distributes sunlight according to a stranger geometry, because its axis lies nearly flat during the journey. For long stretches, one pole points almost straight toward the sun, while the opposite pole faces outward into darkness. The result is not a stronger version of earthly seasons, but a completely different arrangement of light itself. At the pole turned sunward, daylight does not arrive and depart, but simply remains, patient and unbroken, overhead. At the far pole, night does the same, holding its place without dawn, as though morning forgot the address. I think this is where Uranus stops being merely unusual and starts feeling like a world built sideways from time. Because the orbit lasts 84 years, each pole spends roughly half that span in continuous daylight or darkness. So one polar region receives about 42 years of sunlight, followed by about 42 years without any. That is such an enormous interval that ordinary words like summer and winter begin to feel almost decorative. A child could be born during one long polar day there and reach middle age before darkness finally arrived. The sun from that pole would not climb and fall in the familiar way we instinctively expect from skies. Instead, it would drift around the horizon in slow circles, always present, pale, and strangely committed to staying. At the opposite end of the planet, there would be no sunrise to anticipate and no sunset to miss. Only a prolonged darkness, steady and complete, as if the sky had closed one door and forgotten another. I always find it calming that the universe can produce such extremes without any need for drama or noise. Uranus simply keeps rolling onward, carrying these impossible seasons with the same quiet composure it gives everything else. Yet this arrangement does not last unchanged for the entire orbit, and that is where the year becomes richer. As Uranus approaches equinox, the sun no longer favors one pole so completely and begins illuminating the equator more. For a while, the planet returns to something closer to the pattern we would recognize from more familiar worlds. Its roughly 17-hour rotation starts mattering again in an everyday sense, bringing alternating light and darkness across latitudes. Day and night begin taking turns over much of the globe, instead of remaining locked at opposite ends. This more balanced interval is brief compared with the full 84-year orbit, but it changes everything. The frozen arrangement of endless day and endless night loosens, and the planet briefly feels less isolated from comparison. Then, as Uranus continues along its path, the process reverses, and the opposite pole inherits the long light. The old dark hemisphere becomes the bright one, and the bright one slips into decades of shadow instead. It is a beautiful kind of symmetry, though not one any human body would ever call comfortable or ordinary. You might expect such a world to develop severe temperature differences between its bright side and dark side. After all, decades of sunlight on one pole and decades of night on the other sound thermally unfair. Common sense suggests a baked hemisphere and a frozen hemisphere, separated by one of the sharpest climate boundaries imaginable. But Uranus refuses that simple expectation, which is one reason the planet keeps surprising people who study it. Measurements show that temperatures are remarkably even from equator to pole, despite the dramatic imbalance in incoming sunlight. The sunlit regions are not wildly warmer than the dark ones, at least not in the way expected. Somehow, the atmosphere redistributes heat efficiently enough to smooth much of that contrast across the whole planet. Winds and broad circulation patterns appear to move energy around, evening out conditions more than geometry alone predicts. I like this detail because it makes Uranus feel less like a divided world and more like one system. Even tipped nearly over, it still finds a way to share warmth between places that seem destined apart. Exactly how that balancing act works remains uncertain, and the uncertainty gives the planet another quiet layer of mystery. Uranus does not release much internal heat of its own, which makes atmospheric circulation harder to explain completely. On other giant planets, heat rising from within helps stir the air and energize large-scale motion. Here, that interior contribution seems strangely weak. Yet the atmosphere still manages impressive thermal bookkeeping across the globe. Something in the winds, chemistry, or deeper circulation must be carrying warmth where sunlight alone does not. We can measure the broad result, but the detailed machinery remains partly hidden behind distance and limited observation. That happens often in planetary science, where the answer appears first as a pattern and only later. The pattern here is clear enough to trust, even if the explanation still has rough edges. I think there is something honest and soothing about a world that gives us facts before giving meanings. Uranus keeps saying, in effect, this is what happens here, while leaving us to learn why slowly. The seasons also seem to influence when the planet chooses to look active and when it prefers stillness. Voyager 2 reached Uranus near solstice, when one pole was turned strongly toward the sun during prolonged illumination. What it saw was a pale, mostly featureless globe, quiet enough to encourage the idea of dormancy. For years afterward, that image shaped the planet's reputation as the blandest of the giant worlds. But later observations, made as Uranus moved closer to equinox, began telling a livelier and more complicated story. Clouds brightened high in the atmosphere. Faint banding became easier to detect, and dark features appeared briefly. The world had not transformed into something new. We had simply encountered it during a different seasonal mood. That distinction matters because a planet can look empty when it is really just between visible conversations. I have always thought Voyager 2 met Uranus while it was half asleep and politely unwilling to perform. Near equinox, with sunlight redistributed, the atmosphere seemed to wake and reveal a more animated, hidden character. So the tilt does far more than make Uranus photogenic in diagrams or memorable in classroom comparisons. It rewrites the schedule of light, reshapes the meaning of day, and appears to modulate the weather. A place with 42-year daylight and 42-year darkness cannot help becoming meteorologically distinctive. Even the question, what time is morning, becomes slippery there, depending on latitude and season together. Near equinox, morning and evening return in a recognizable rhythm as the planet rotates beneath the sun. Near solstice, especially toward the poles, that rhythm dissolves and the sun simply circles without setting. The clock remains, but the familiar cues attached to it are partly erased by geometry. That is one of those details I find quietly profound, because it changes the experience of duration itself. Uranus does not merely have unusual seasons. It lives inside a different arrangement of repetition and pause. And all of this traces back to a single fact that still points toward some ancient intervention. A planet does not normally end up in this posture by accident of ordinary formation alone, at least. Worlds inherit their basic spin from the rotating disk of gas and dust that built the system. That shared beginning is why most planets keep roughly similar orientations, even with their smaller individual variations. To tip a giant world almost onto its side requires changing that inherited spin in a major way. The leading explanation is straightforward in outline, even if the event itself would have been unimaginably violent. Early in solar system history, Uranus may have been struck by a protoplanet 1 to several times Earth's mass. Not a head-on collision, but an off-center impact, delivering angular momentum in the wrong direction. That kind of glancing blow could reorient the planet without necessarily destroying it or scattering everything permanently. I think this idea persists because it feels physically serious enough to match the scale of the outcome. A world this massive does not lie down because something brushed past it. Something substantial had to intervene. There is a useful way to picture the problem without turning it into a page of equations. A spinning planet behaves a little like a gyroscope, resisting changes to the direction of its axis. The larger and heavier the world, the harder it is to redirect that stored rotational commitment. Uranus contains about 14.5 Earth masses, which gives it enormous inertia against being reoriented. A small impact would leave only a scratch on the story, not a new planetary posture. To produce a tilt near 98 degrees, the intruding body had to bring real authority. That is why researchers describe the impactor as a protoplanet, not an oversized asteroid or stray moon. Computer models show that a collision of this scale can reproduce something very close to Uranus today. Some versions use one giant strike, while others allow several somewhat smaller impacts, adding their effects together. Either way, the common idea is clear. Uranus was not born sideways, but pushed there by force. That possibility becomes even more persuasive when you remember how crowded the young solar system once was. The giant planets formed in a rough neighborhood full of leftover building blocks, crossing paths and exchanging trouble. Large icy bodies were more common then, and collisions between growing worlds were far likelier than today. Our own planet probably suffered a giant impact early on, one tied to the Moon's formation. So a major collision at Uranus would not be an isolated absurdity, only an extreme surviving example. In that early era, planet building was less like careful architecture and more like weather in stone. Worlds merged, scattered, and occasionally struck at speeds that could rewrite their futures in a single afternoon. What happened to Uranus may simply be one of those final, violent edits that never got undone. I find that oddly comforting, because even cosmic disorder eventually cools into something stable and almost graceful. But if a blow that large really happened, there is an obvious problem waiting quietly beside the theory. A collision strong enough to knock over a giant planet sounds like the kind of event that should leave chaos behind, not the tidy system of rings and moons Uranus actually keeps today around itself. If the planet was hit hard enough to alter its axis so dramatically, what happened to everything nearby? Why are the major moons arranged so neatly in the tilted equatorial plane instead of scattered or misaligned? Why do the rings look confined and organized rather than shredded into a confused halo of debris? That tension is where the story becomes more interesting, because the evidence seems calm while the cause sounds savage. Somehow, a violent beginning had to lead to a remarkably orderly outcome, and that is not trivial. The next step is to ask whether the very neatness of the Uranian system might preserve the answer. Because sometimes in astronomy, what first looks like an argument against an idea becomes its strongest support. And with Uranus, the question is no longer whether something struck it, but how order survived the blow. That neatness is exactly what makes the collision idea harder, and strangely enough, more convincing at once. If Uranus had simply tipped after its moons were already settled, those moons should have ignored the planet's new posture. They would have kept circling in their old plane, loyal to the earlier spin, not the later sideways arrangement. Instead, the major moons move in tidy, nearly circular tracks that line up closely with Uranus's tilted equator. The rings do the same, keeping to that same steep plane with a discipline that feels almost deliberate. At first glance, order like that seems to argue against any ancient upheaval, because chaos should leave obvious scars. But planetary systems often preserve history through arrangement rather than damage, which I think is easy to underestimate. The moons are not just ornaments around Uranus, but witnesses whose paths still reflect something about the past. Their geometry says that whatever happened here did not merely disturb the system and then walk away. It changed the planet and somehow set the whole nearby family into the same new orientation afterward. That is why timing matters so much in this story, perhaps more than force alone ever could. If the moons were older than the tilt, they should have remained noticeably misaligned after the planet was knocked sideways. A planet can change its spin axis quickly, but distant moons do not instantly follow that new direction. They keep moving through space according to the old arrangement, unless some later process brings them into line. So the clean alignment we see today suggests the main system formed after the tipping, not before it. In that picture, the collision did more than tilt Uranus. It also created the raw material for rebuilding. A glancing impact could have blasted huge amounts of ice and rock outward without letting that debris escape entirely. Held by Uranus's gravity, the material would spread into a flattened disk around the planet's new equator. Over long spans of time, that disk could slowly gather itself into moons, rings, and smaller companions. What looks calm now may be the patient end state of something once violent, which feels very true of nature. This idea also helps explain why the major moons travel on such orderly, nearly circular paths around Uranus today. Bodies that form inside a disk tend to inherit that disk's shared plane and its general smoothness. They collide, exchange energy, and gradually settle into more regular orbits as the system cools down. So if a debris disk formed after the impact, the moons born from it would naturally match Uranus's new tilt. They would not need to be dragged along during the catastrophe, which would have been much harder to arrange. They would simply arise already aligned, because the disk itself had already accepted the planet's changed orientation. That is one reason simulations of giant impacts remain persuasive even after the neat moon system is considered. When researchers model a strike and then let the debris settle, they can produce something much like Uranus. The order we see is not a contradiction, but possibly one of the strongest fingerprints of the event. I always like when a problem turns inside out and becomes evidence, because it makes the universe feel sharper. Not every moon around Uranus fits this picture equally well, and that distinction matters more than it first seems. The larger inner moons are the ones that track the tilted equator most faithfully and most cleanly. Farther out, some smaller moons follow stranger paths that are more stretched, tilted, or otherwise less orderly. Those distant objects may not share the same origin story as the main family close to the planet. Some are likely captured bodies, wandering objects pulled in later and never fully folded into the main pattern. That kind of split is common around giant planets, which often keep a tidy inner household and rougher outskirts. So the odd outer moons do not weaken the broader case for impact and rebuilding near the planet itself. If anything, they help separate the quiet, disk-borne system from later additions acquired under different circumstances. The inner family tells the clearest story, because it speaks with one voice about the planet's tilted equator. And once you start listening to that inner order, The next mystery opens below the clouds instead. Uranus is not a world with a surface waiting beneath the haze, and that changes how we should picture it. There is no ground there in the ordinary sense, no continent, no crust, no place to stand and look around. If you could descend through its atmosphere, you would simply pass into denser and hotter material without meeting a floor. The outer region is mostly hydrogen and helium, the same light ingredients common in the giant planets generally. Mixed into those upper layers is methane, which helps give Uranus its pale blue-green color from far away. Lower down, the pressure climbs steadily until gases stop behaving like familiar air and become dense fluid instead. The transition is gradual rather than sharp, which makes the planet feel less built in layers than graded. I have always found that unsettling in a peaceful way, because it removes the comfort of clear boundaries. Uranus is more like a deepening body of matter than a world with an outside and inside. And beneath that outer envelope lies the region astronomers call ice, though the word needs careful handling here. In planetary science, ice does not always mean something cold and solid like a winter pond at all. Here, it means materials such as water, ammonia, and methane compressed into exotic forms by enormous internal pressure. Those substances are not sitting there frozen in neat blocks, but moving as hot, dense, electrically active fluids. The term survives because it describes chemistry more than texture, which is one of those scientific habits you learn. Deep inside Uranus, these materials likely make up most of the planet by mass, beneath the lighter atmosphere. Under conditions like that, familiar substances become unfamiliar quickly, and ordinary intuition stops being especially useful there. Water does not behave like water in a glass, and methane does not remain a simple gas. Everything is squeezed, heated, and rearranged into states we do not encounter naturally anywhere on Earth. Popular science sometimes mentions diamond rain here, and that image may hold some truth without being fully settled. Carbon from methane could be compressed into diamond-like material and sink slowly downward through the interior darkness below. At the center, Uranus probably contains a denser core, made mostly of rock and metal under crushing conditions. It may be roughly Earth-sized, though hidden beneath many thousands of miles of fluid layers above it. Whether that core has a sharp boundary or fades gradually into the surrounding material remains less certain. We infer its presence because Uranus has too much mass to be explained by light gases alone. By measuring the planet's size and its pull on moons and spacecraft, astronomers estimate its overall density. That density falls between rock and gas, which points toward a large interior made of heavier, volatile material. From there, physics does the rest, using gravity, pressure, and magnetic clues to sketch the hidden structure. We have never seen inside Uranus directly, of course, but planets can still be read from outside. I think that is one of astronomy's quiet triumphs, learning interiors from motion, fields, and a few stubborn numbers. And in Uranus, that unseen interior may connect directly to another puzzle, just as strange as the tilt. Compared with the other giant planets, Uranus gives off surprisingly little heat from its own interior today. That might sound minor, but it makes Uranus stand apart from worlds it otherwise resembles in important ways. Jupiter, Saturn, and Neptune all radiate more energy than they receive from sunlight alone across long timescales. They are still leaking leftover heat from formation, slowly cooling after the violence of their early assembly. Neptune is especially striking because it emits well over twice the energy it gets from the Sun. Yet Uranus, despite being broadly similar in size and composition, seems to radiate only a little extra. Its upper atmosphere is therefore extraordinarily cold, even colder than Neptune's, despite being closer to the Sun. That is the sort of mismatch scientists notice immediately, because near twins are not supposed to diverge so sharply. Something about Uranus either removed much of its internal heat long ago, or prevents that heat escaping now. The missing warmth does not announce itself dramatically, but it may be one of the planet's deepest clues. One possibility is that the same impact that tipped Uranus also drove out a great deal of stored heat. A blow large enough to rearrange a giant planet would inject immense energy and disrupt the interior profoundly. In the aftermath, Uranus may have lost much of its leftover heat faster than Neptune ever did. If so, the planet has been running comparatively cold ever since, having spent that thermal inheritance early. Another possibility is subtler, and in some ways even more interesting than simple heat loss after impact. The collision may have left Uranus internally layered in a stable way that suppresses large-scale mixing. Normally, hot material rises and cooler material sinks, carrying heat upward through convection inside giant planets. But if the interior is divided into compositionally stable layers, that churning can be greatly reduced. Mixing is suppressed, the deep heat stays trapped below, and the outer planet remains colder than expected. I like this explanation because it turns stillness itself into the mechanism, not absence, but confinement instead. That comparison with Neptune keeps the question alive, because Neptune seems to do what giant planets usually do. It leaks internal heat effectively, drives stronger weather, and does not share Uranus's same thermal quiet. So if Uranus and Neptune began as near siblings, then something important must have separated their later histories. A giant impact can tie several oddities together at once: the tilt, the rebuilt moon system, and missing heat. That economy is why the collision model remains so attractive even with its unresolved details and complications. Still, science is healthiest when it keeps a little room for alternatives, especially around distant, poorly visited worlds. Perhaps the heat was lost, or perhaps it remains trapped under stable layers, or perhaps both are partly true. Perhaps the moons formed from impact debris, or perhaps some were guided into place by a later disk. The story holds together beautifully, but beauty is not proof, and I think that distinction matters. Beyond the collision, quieter possibilities still wait in the dark, and that is where Uranus becomes mysterious again. That is where the story opens back up, because not every sideways world must begin with one catastrophic afternoon alone. Some researchers imagine Uranus once orbited with a very large moon, exerting a slow, persistent gravitational pull nearby. Given enough time, that pull could torque the planet's spin axis through resonance instead of through impact alone. Resonance is one of those patient tricks in physics, where small nudges accumulate because the timing keeps matching. If a moon's orbital rhythm lined up with Uranus's natural axial wobble, the tilt could gradually grow enormous. In that version, the planet is not violently knocked over, but slowly persuaded into a stranger posture across ages. The difficulty, of course, is that such a moon would need to be massive and then disappear convincingly afterward. Perhaps it was ejected, perhaps destroyed, perhaps swallowed into some later reshuffling we can no longer directly reconstruct. I find the idea elegant in a ghostly way, because it asks an absent object to explain everything. It is the kind of explanation astronomy sometimes permits, though only reluctantly, when the evidence points towards something missing. A related possibility comes from the early migration of the giant planets through the young solar system's unsettled architecture. There is strong reason to think those outer worlds did not always occupy the exact paths they follow today. As orbits shifted, Uranus may have crossed a gravitational resonance capable of amplifying a modest original tilt dramatically. In plain terms, the planet's own slow wobble could have been pumped larger by the changing rhythm around it. A surrounding disk or a substantial moon might have provided the leverage needed for that process to work efficiently. This is a gentler picture than a giant impact, but not a simple one by any means. It replaces one dramatic collision with a long choreography of timing, migration, and gravitational persistence over millions of years. I like that possibility, because it reminds us the solar system was once less like clockwork than construction. Even so, these quieter models must explain more than the tilt itself if they hope to rival the collision story. They have to account for the broader oddness of Uranus without borrowing too much from coincidence. That is where Neptune becomes especially useful, almost like a control case set quietly beside its stranger sibling. Neptune formed in the same cold outer region from roughly similar materials and grew to nearly the same scale. Yet Neptune did not end up lying on its side, and it did not lose itself in the same peculiar way. Its axis is tilted only modestly, well within the broad family pattern shared by the other major planets. Whenever two worlds are so alike in build, yet so different in posture, the difference starts carrying real weight. A chance impact explains that contrast easily enough, because one planet can be struck while another is simply not. The gentler mechanisms have a harder task, since they must explain why Uranus alone was captured by those special conditions. That does not make them impossible, only less economical, and science usually notices economy when several explanations compete. To me, Neptune's quiet normalcy makes Uranus seem even stranger, as if one twin kept the script while the other improvised. And because the collision also helps with the moons and missing heat, it still keeps its place at the front. Yet even if the tilt were solved tomorrow, Uranus would remain oddly misaligned in another invisible and unsettling way. Like the other giant planets, it generates a magnetic field, but its magnetic arrangement is anything but tidy. On many worlds, a magnetic field lines up fairly closely with the spin axis, as though the planet's compass agrees. Uranus does not behave that way, and the disagreement is large enough to feel almost personal. Its magnetic field is tilted about 59 degrees away from the rotation axis, a severe off-axis slant. That means the magnetic poles sit nowhere near the geographic poles in the ordinary comfortable sense we expect. If Earth behaved this way, Compasses would still work, but the geometry behind them would look much less polite. I have always thought Uranus feels like a planet where even the invisible furniture has been pushed askew. The spin axis leans one way, and the magnetic field points somewhere else, as though agreement was never part of the design. The field is not only tilted off-axis, but also shifted away from the planet's center by a surprising amount. On a more orderly planet, the magnetic field behaves roughly as if it were generated near the middle. Uranus, instead, seems to produce magnetism from a source displaced noticeably to one side inside the world. So the field is both crooked and off-center, which gives the entire magnetic environment a lopsided quality. As the planet rotates, that unusual geometry makes the magnetosphere swing around in a complicated, tumbling fashion. The magnetic bubble does not sit there like a neat bar magnet planted in space around Uranus. It twists, opens, and reorients as the planet spins beneath it, changing its presentation to the solar wind constantly. That must make the surrounding space environment remarkably dynamic, even if the planet itself looks placid from afar. I think there is something deliciously eerie about a calm blue world carrying such a badly behaved invisible compass. It is another reminder that Uranus often looks simplest exactly where it is most peculiar. The best explanation points inward to where that field is probably being made, deep below the visible atmosphere. Earth's magnetic field comes from a churning metallic region near the center, which encourages a relatively organized global structure. Uranus likely generates its field in a different place entirely, within a shell of electrically conductive exotic fluids. Those fluids are thought to include high-pressure water, ammonia, and related materials behaving in ways no kitchen ever demonstrates. If magnetism is being produced in a thinner conductive shell rather than a broad central metallic core, strange geometry becomes easier. A shell dynamo can yield a field that is offset, irregular, and strongly tilted relative to the spin axis. That fits Uranus rather well, though it does not yet answer every detail about the field's exact shape. The deeper truth is that we have only a brief, direct measurement of this magnetic oddity from one passing spacecraft. I find that astonishing, because we built a whole portrait of a crooked magnetosphere from a very short encounter. It leaves open the question of how much stranger the field might look if we actually stayed long enough. The same world that hides a skewed magnetosphere also wears one of the gentlest colors in the solar system. Uranus appears pale blue-green because methane, high in the atmosphere, absorbs red wavelengths from incoming sunlight very effectively. What remains to scatter back outward is richer in blue and green, so the planet keeps that cool, watery tint. It is not the bright cobalt of Neptune, but a softer, calmer shade, almost as if the color were speaking quietly. A high haze layer helps create that effect by muting contrast and softening whatever lies below. Through that haze, the atmosphere looks smoother than it really is, which long encouraged the impression of a bland planet. I have always liked how chemistry can become mood at planetary scale, turning a gas into a visual personality. Methane removes the warm tones, and haze blurs the details, leaving Uranus with a face that seems almost restful. But that peaceful appearance is partly a trick of atmosphere, not proof that nothing happens underneath. In some ways, the color of Uranus is a veil, and veils are interesting precisely because they conceal. Beneath that softened blue-green face, Uranus carries a ring system far narrower and darker than Saturn's famous architecture. Its rings are thin, dim, and easy to miss, more like charcoal lines than glowing bands of polished ice. There are more than a dozen known, each tracing the planet's tilted equatorial plane around the sideways world. Because the particles are dark and not especially reflective, the rings first reveal themselves through starlight interruptions rather than spectacle. They stay sharply confined, in part because of shepherd moons, small companions whose gravity corrals wandering ring material. I love that phrase, shepherd moons, because it sounds almost too gentle for orbital mechanics, and yet it is exactly right. Those little bodies help keep the rings narrow, instead of letting them smear into a broad, diffuse sheet. Uranus also has more than 24 moons altogether, ranging from tiny, irregular objects to substantial icy worlds. Some of the outer ones are likely captured moons, later arrivals that never fully joined the tidy inner family. Even here, the system divides into order near the planet and rougher company farther away. The 5 major moons are Miranda, Ariel, Umbriel, Titania, and Oberon, and their names come from Shakespearean worlds. That naming choice feels unusually literary for planetary science, though in English it lands naturally and almost charmingly. These are not gods from ancient myth, so much as figures borrowed from plays and poems, circling a tilted planet. Ariel appears brighter and more geologically reworked than some of the others, while Umbriel looks darker and more somber. Titania and Oberon, the largest pair, carry old scars and long histories written across icy, cratered surfaces. I think moon systems become more memorable once the names stop sounding like labels and start sounding like company. Around Uranus, that company feels especially intimate, because the whole family shares the planet's tipped equatorial plane. They move in that steeply turned arrangement as though the sideways posture were the most natural thing imaginable. Their orbits preserve the geometry of Uranus's history more faithfully than any visible wound on the planet itself. And among them, one moon stands apart so strongly that it almost seems to belong to a different imagination. Miranda is the moon that makes people stop and look twice, because its surface appears assembled from incompatible pieces. Instead of one consistent landscape, it shows a patchwork of terrains pressed together with startling abruptness. Some regions are grooved and ridged, others smoother, and the boundaries between them can look almost stitched. It also carries enormous cliffs, among the tallest known anywhere in the solar system, despite Miranda's modest size. For such a small moon, that is genuinely uncanny, like finding mountain ranges on something that should have stayed simple. One idea is that Miranda was shattered long ago and later reassembled under its own gravity into this mismatched form. Another is that tidal heating and internal upheaval reshaped it from within, creating those bizarre provinces without complete destruction. I have always found Miranda endearing, because it looks less polished than the other major moons, almost experimental. It is a reminder that small worlds can keep very strange histories when gravity and time work together patiently. And because we have seen it only briefly, Even Miranda's broken face remains partly a first draft. That is perhaps the most important feeling to keep as we move onward. Almost everything here is still provisional. We have one flyby, a handful of seasons watched from far away, and a planet that keeps offering questions faster than closure. The alternatives to collision remain alive. The magnetic field remains only partly mapped, and the moon system still holds unresolved stories. Even the calm blue-green appearance depends on atmospheres and angles we have sampled far less than we would like. For a major planet, Uranus has been studied from close range astonishingly little, and that thinness changes everything. I think that is why the planet feels so compelling rather than merely obscure, because ignorance here still has shape. We know enough to see the pattern, but not enough to settle every cause, and that is a beautiful place for science. A world this strange deserves more than one hurried visit, and the fact that it has not had one yet lingers. The next question is no longer only what Uranus is like, but how little time we have actually spent there. That thinness becomes impossible to ignore once you remember how little direct time humanity has actually spent there. Voyager 2 remains our only close visitor to Uranus, and even that encounter was only a swift passing one. It traveled for years across the outer solar system, then crossed the Uranian system in only several brief hours. No spacecraft has ever entered orbit there, and no atmospheric probe has ever fallen through those pale clouds. For a major planet, that is astonishingly little attention, almost like judging an ocean from one shoreline glance. Uranus circles about 19 times farther from the Sun than Earth does, deep in a dim and patient cold. By the time our lone visitor arrived, it had already spent years simply crossing the distance to get there. And when the meeting finally came, the whole close conversation was over almost before it could properly begin. I always find that contrast moving, the long approach followed by the briefest possible exchange with a giant. Nearly everything we know from nearby still rests on that one hurried encounter and the careful watching since. That single flyby gave us a remarkable amount, but it also fixed our first impression at a misleading moment. Voyager 2 arrived near solstice, when Uranus was showing one of its quietest seasonal faces to the Sun. The spacecraft saw a smooth blue-green globe with very little visible weather and almost no dramatic atmospheric texture. For years, that image encouraged the idea that Uranus was sleepy in the dullest possible planetary sense. Later observations from Earth and from orbiting telescopes slowly corrected that first calm portrait with better timing. As the planet moved toward equinox, bright clouds appeared, faint banding emerged, and darker features came and went. The world itself had not changed character so much as our angle and season had changed axis. That matters, because a first impression can harden into reputation long before a planet has fully introduced itself. I think Uranus suffered slightly from being met during a quiet mood, and then judged by it. What we have now is not a complete picture, but a better one, and still only partial. The unanswered questions begin with the oldest one, which is still the simplest to ask and hardest. Exactly how Uranus was tipped, and exactly when, remain unresolved despite the strength of the collision story. A giant impact still explains the most with the fewest moving parts, which is why it leads. But whether there was one great blow or several smaller ones working together is still not settled. The broad outline feels sturdy, while the finer mechanics remain just beyond what present evidence can firmly hold. We also still do not know why so little internal heat escapes from the planet today. That missing warmth may have been blasted away long ago, or trapped beneath stable interior layers instead. Both ideas fit much of what we can measure, and neither has yet won complete certainty. I like that honesty, because it keeps the mystery real, rather than pretending the gaps are decorative. Uranus still withholds the exact terms of its accident, and science is wise enough to admit that. The magnetic field adds another unanswered chapter, and it is one of the strangest chapters in planetary science. We know the field is steeply tilted and offset from the center, but not precisely why. The leading picture places its source in a shell of conductive exotic fluid, rather than a central core. That idea makes the crooked geometry easier to understand, though it does not explain every detail cleanly. To really map such a field, we would need long observation through many rotations from nearby space. A flyby can reveal that something is unusual, but not patiently chart the full behavior of it. The same is true of the moons, especially the possibility of hidden oceans under icy outer shells. Some of Uranus's satellites may hold subsurface water, but our present evidence is far too thin. Miranda also keeps its own secrets, because its broken patchwork surface still resists a single agreed history. I think that little moon looks like a question mark made out of cliffs and frozen memory. All of this is why Uranus is often described in American space policy language as a high priority for future exploration. The case for returning is not sentimental, though I admit the planet invites a certain tenderness anyway. A dedicated orbiter could stay for years, not hours, and watch the system in motion properly. It could study the atmosphere through changing seasons, follow the magnetic field through complete rotations, and monitor weather. It could measure the planet's gravity in detail and test competing ideas about the hidden interior. It could examine the rings and moons up close, instead of relying on distant glimpses and inference. And if paired with an atmospheric probe, the mission could directly sample gases as the probe descended. That would tell us far more about composition, temperature, pressure, and winds than remote sensing alone can. I always think of orbiters as patient listeners, which is exactly the kind of witness Uranus deserves. After one hurried hello, the next step should be a long stay and a much more attentive conversation. Getting there, of course, is not simple, and distance is only the first part of the difficulty. A mission to Uranus must cross an immense gulf and keep working far from the sun's warmth. Out there, sunlight is weak enough that ordinary solar power becomes a much less practical choice. A spacecraft would need long-duration power sources suited to the deep outer solar system environment instead. That requirement alone makes such missions more demanding, more expensive, and slower to move from dream to launch. The travel time would also stretch across many years, asking for unusual patience from planners and scientists. From proposal to arrival to final data, the whole effort would be measured in decades, not seasons. Yet some questions are worth that kind of patience. especially when the world in question has waited longer. I find there is something fitting about a slow mission to a planet defined by long, quiet intervals. Uranus does not reward hurry, and perhaps that is part of why it continues to elude us. If such a mission comes, it could answer several mysteries at once, instead of nibbling around them separately. An orbiter could test whether the interior is truly depleted of heat, or merely holding it captive. It could watch how the magnetosphere changes through time, and build a real three-dimensional map of it. It could search the moons for clues of buried oceans, internal activity, or ancient reshaping by tides. An atmospheric probe could fall through the upper layers and taste the chemistry directly as it descended. That kind of descent would be brief, but brief in the fruitful way lightning is brief. For a short time, the probe could read pressure, temperature, winds, and cloud structure from inside. Those measurements would anchor everything we infer from above and turn guesswork into much firmer understanding. I think the most exciting missions are the ones that change the grammar of a whole subject. A proper Uranus mission would do exactly that, replacing one snapshot world with a lived-in planetary system. Until then, we remain in a thoughtful middle ground, informed enough to speak clearly, limited enough to stay humble. We know Uranus lies on its side, and we know that fact shapes nearly everything else about it. We know Voyager 2 passed by once after years of travel and stayed only for hours. We know no orbiter has ever remained there, and no probe has yet entered its atmosphere. We know the planet is far away, the sunlight thin, and the engineering demands unusually serious. And we know the major open questions with surprising clarity, which is its own kind of progress. What we do not yet have is the close, lingering evidence that would tie every thread together. I have always thought uncertainty feels gentler when its boundaries are named instead of hidden from view. Uranus gives us exactly that kind of honest uncertainty, shaped clearly enough to invite return. It is not a blank world anymore, only an unfinished one, and there is a difference. So the story comes back at last to the plain fact that started everything and quietly governed the rest. Uranus alone among the major planets lies nearly flat as it circles the sun through darkness. From that posture come the long polar days, the tilted moons, the unusual seasons, and the quiet cold. The leading explanation remains an ancient collision, perhaps one glancing strike, perhaps several near the beginning. That event may have tipped the planet, helped shape its moon system, and altered its internal heat. Other possibilities still remain alive, and a careful mind leaves room for them without embarrassment. But whatever the exact mechanism, something changed Uranus profoundly, very early, and the planet never changed back. I think that is why the world lingers emotionally after the facts have all been spoken. Its mystery is physical, yes, but also strangely graceful, because the aftermath has been so calm. The violence, if violence there was, lasted briefly, and the stillness afterward has lasted almost forever. That may be the gentlest thing Uranus offers at the end of a long, quiet night like this. Not every tilt has to be corrected, and not every old disturbance has to be undone. A world was knocked sideways near the dawn of the solar system and simply kept going. its seasons adjusted, its moons gathered into place, and its long life continued in another posture. There is comfort in that kind of endurance, especially because the planet does not seem troubled. It does not struggle to stand upright again or apologize for the angle it keeps. It just turns, pale and patient, carrying its altered history without complaint through the cold dark. If you enjoyed this slow journey, a like or subscribe helps the channel find fellow night travelers. And now you can let the sideways world drift softly to the edge of thought and rest. Out there, Uranus remains at peace, and here, for tonight, you are allowed to be peaceful too.